Hello everyone and welcome to episode 3 of Explaining Physics Concepts. In this video we're looking at part 2 of simple harmonic motion, and we will only be looking at damping and one past paper question. So let's begin. When I say damping, I think the word itself is pretty self-explanatory, because when we say damping is when there is a reduction in energy, right? So if I were to write it in proper words, it is the reduction in the energy slash, or you can say amplitude as well. It is the reduction in the energy amplitude of oscillations by resistive forces. One example that I love to give to my students, because that helps them a lot, is let's say you're sitting on a swing and you start off strong. You have a very fast swing in the beginning, but then if you do not give any push in the middle of the swing, you'll see how it gradually dies out and it then comes to a halt, right? That is what damping is. There are resistive forces, there's air resistance, and then there's you can have water resistance in water, and also you can have friction, etc. as well, right? Now this is what damping was. Or you can also think of it when you have an oscillation. Let's say you have a pendulum and then you start moving it, you'll see how it gradually comes to a stop because of the resistive forces, that is air resistance in this case. Now we will be looking at 3 kinds of damping, but before that we will be looking at 3 kinds of oscillations, right? What is oscillation, what 3 kinds of oscillations are. So I'll just draw and then we'll see. Number 1 is what are the 3 kinds of oscillations. So first up we have free oscillation. You'll see why we're doing oscillations first and then damping, because it will then have a more link between them. Free oscillations. Okay, I'll type this out so that it's faster that way. Okay, so free oscillations, I'll say, what are free oscillations? It is when an object vibrates at its natural frequency. It is when an object vibrates at its natural frequency. It's not something very difficult. You just see the word free and then that means there are no external forces and hence no energy lost. There are no external forces. There are no external forces and hence no energy loss. This is only possible in a vacuum. If you have a pendulum in a vacuum, there are no resistive forces in that, so it will never come to a stop. That is what it means. It will keep oscillating until you take it out from the vacuum. Oh no. Why did it get so smaller? Okay. Wait, let me write it here again. Okay. Next up we have damping oscillation. Damped oscillation, you can just say. Damped oscillation. Again, the word damp itself tells you an oscillation where there are resistive forces. Okay? So we can just have what we can say, motion that is not free from external forces, and dies out gradually. Again, you can take an example of the pendulum or the swing as well. And the next one, the last one actually, is forced oscillation. Forced oscillation. Again, the word force tells you that the body is made to vibrate by an external force. Body is made to vibrate by an external force. That is to say, if when you're sitting on a swing, you have to give it a push. You have to give it an initial push to get it started. That is what is forced oscillation, and then it gradually dies out. That is damped oscillation, and if it was in a vacuum, then again that was free oscillation. Now we're gonna move on to 3 kinds of damping. Now, first up we have light damping. Now, light damping, that gradually damps out, that gradually dies out, and I would this will be better explained through graphs, so I'll just draw graphs now. Okay, for light damping, the motion starts off strong and then it gradually dies out. So you see how it starts off strong and then the resistive force is acting and then it gradually dies out. But if you're talking about heavy damping, if we talk about heavy damping, again, it is relatively more stronger than light damping, that there is suddenly an external force and then the object is made to stop suddenly, so but it still takes a lot of time. So if I were to draw this graph, this will be like this. It starts off strong and then it takes time to die out, right? This is how this will look. And if you look at critical damping, now you can see how the strength of the words, it increases. First you have light, then you have heavy, and then you have critical. Is like it stops immediately. So if you look at its graph, you'll see how if it starts here, it just stops like this. It just stops that moment, in that exact place. But when it comes to heavy damping, yes, it does stop immediately, but it still takes a time to die out. And light, it just takes a lot of time to die out. So these were the graphs to explain damping. Now, another part that comes, I would say, under damping is this. Resonance. Now, what do we mean by resonance? Let me first write the definition as it is mentioned in our syllabus. So the resonance, it's a phenomenon where the amplitude of oscillation becomes maximum when the frequency of the driving force is equal to the natural frequency of the system. So in simple words, when the natural frequency of the object matches the driving force. So there's a driving force and then there's natural frequency. When the frequencies of these two matches, that is when the amplitude becomes the maximum. Let me give you a very simple example. You have let's say you food on your plate, and when you place that food in the microwave, you'll see how the food particles, they have natural frequency. And then when you place it in a microwave, the microwave has a driving frequency. So the heat from the microwave has its own driving frequency, and when these two frequencies, when they match, that is when its amplitude is maximum. It gets very hot. And another graph that I'll draw and I'll explain it to you is when you see damping, you'll see something how it changes over time. Let's say, okay, let's assume this is where my natural frequency is. I'm just going to write as natural frequency, and this is where my driving frequency is. So in case you don't forget, its natural frequency is natural frequency and driving frequency is driving frequency. Now we are going to draw, let me make it very clear. Now, you start off strong, like this, and then you start from the same spot, and then ending at the same spot. Now, if I were to label all of these, this is light damping. This is, okay, no, this is light damping, my bad. This is no damping, and this is, you can say, damping, it just increases, or you can say heavy damping or critical damping. Now, the purpose of this graph is to tell you the relationship between frequency and damping. Now, you'll see, what are a few things that you notice? Number one, this is the amplitude. The amplitude, it decreases. Let's just make points ourselves. Number one, amplitude decreases with damping. Number two, the peak, do you see how it started off with a sharp peak and then it broadens and then it shifts to left? So peak, I'll consider at one point, peak broadens plus it shifts to the left. So you started off on this part, and then you see it got here, and then it started moving to the left. It decreased, it became more broad. So these are the things that happen when damping occurs. But what happens to the frequency? And that is where I see a lot of students getting confused. Frequency, and this is, I think I should write it. Frequency is not changed by damping. Frequency is not changed by damping, and let me explain it to you through an example. Now, first of all, for that you need to understand what frequency is. Frequency, Number of oscillations happening per unit time. Right? And amplitude is, you know, the maximum displacement. Now let's say you have a swing, and then when you're on a swing and you start off like this, then you go back. So and let's say it's taking 1 second to complete, you know, to go from here and then go from here. And that is, you say that initially 1 second is taken and the amplitude is very great, but over time with resistive forces, you'll notice how the swing, it gradually dies out and it gets slower and slower. In that time, the amplitude, if you're reaching this point, you start reaching this point, it starts slowing down, the amplitude decreases, but the time for you to go from here to here, it remains 1 second. That does not change, and that is why frequency remains the same as well. And I hope that made sense. Now that we're done, we have actually completed this chapter. Now we're going to do one example question, and that example question is, okay, the example question is summer 2018 paper 4-3 question number 2. Okay, now let's see what the question says. A metal plate is made to vibrate vertically by means of an oscillator as shown in figure 2.1, and in the figure they have given us an oscillator like this. Some sand is sprinkled and then there's some, you can say, sand on it. The variation with displacement y of the acceleration a of the sand on the plate is shown. And now if you see the graph, you'll see we have already done this graph and we've already discussed this graph as well. It's a graph of acceleration against displacement, and the graph is a straight line, a negative gradient straight line too, like this. And the A part says use figure 2.2 to show how it can be deduced that the sand is undergoing simple harmonic motion. Pretty simple. Now what I would want you to do is A part. What is simple harmonic motion? Simple harmonic motion, the displacement from a fixed point is directly proportional to the acceleration from a fixed point, but in opposite direction, and that is literally what is translated in this graph. First of all, when you have, first we'll say, since it's for 2 marks, first point is, it's a straight line through origin. It's a straight line through origin. Every time you see a straight line through origin, that means acceleration is directly proportional to displacement. Number 2, this is one part of the simple harmonic motion definition, that acceleration from a fixed point is directly proportional to displacement. The second part says but in opposite direction, which means the negative gradient, so you see this is a negative gradient, the positive gradient would have looked like this, but this is a negative gradient. Negative gradient suggests that acceleration and displacement are in opposite direction. And see, this is how simple it was. You just had to look at the definition, then you just had to see how the definition was quite literally translated into a graph, how they're proportional and how they're, it's a negative gradient that suggests they're opposite direction. Second question, calculate the frequency of oscillation. Now they're asking for us to calculate the frequency of the oscillation of the sand. Now, if you see what is acceleration, acceleration is minus omega square x naught, right? We have done this question in the beginning, and the reason why I'm not adding sign in here is because we will be looking at maximum acceleration. Now, if you look at the graph, we'll take the value for the maximum acceleration, which is 4.2, 4.5. So this is 4.5, and then omega square, omega is 2 pi f square, and x naught is the amplitude. And do you see what the amplitude is? It's -8, or you can have 8. So we'll take 8 into 10 raised to the power -3 because it's in millimeter. And when you solve this, you will get, and then when you have to remove the square and all of that, you get frequency as 3.8 hertz. And then the B part, the amplitude of the oscillation of the plate is gradually increased beyond 8 millimeter. The frequency is constant. At one amplitude, the sand is seen to lose contact with the plate. State the position of the plate. Now, I think the best way to explain this is if you take your hand and you put some pieces of paper on it and you start moving it with, a lot of energy and frivolously, you'll see the paper starts losing its contact the moment you thrust your hand up. So above, so we'll say it loses its contact above the equilibrium. And then for the second part, calculate the amplitude of the oscillation. Now, if you have noticed, the moment the thing stays dropped from certain thing, their acceleration in that point is 9.81, right? If you see, we have done this a lot as well. The moment something drops, the moment something leaves its surface, at that point the acceleration is 9.81, because at that time the entire acceleration, the weight is acting in the downward direction and there are no resistive forces. So at that point acceleration is 9.81, and then gradually as they move down, as they move up, resistive forces start taking place. So 9.81, and then again we'll have 2 pi f times x naught. Again we'll apply the same formula, and then you'll have the amplitude as 17 millimeter. And I hope that helped, and if you have any questions, feel free to comment.